In this lecture today, we talk about probability distributions. We first talked about random variables, discrete distributions, and then finally some of practice. Now, what is a random variable? A random variable is a variable of which possible values are numerical outcomes of a random phenomenon. Some examples include the amount of time a machine is idle for, or the salary of a graduate from our program, or the number of heads that face up when you toss 10 coins. There are two main types of random variables: discrete variables and continuous variables. A discrete variable is one of which the outcomes come from a counting process, such as the number of classes that you are taking. A continuous variable is a variable of which the outcomes come from a measurement, such as annual salary or the height and weight, etc. Here are some notations. A random variable x is an uppercase letter. An actual value of the variable is a lowercase x. The probability of a variable x taking value lowercase x is simply p of x, or p of uppercase x equal to lowercase x. Sometimes when we have multiple variables, then variable names are in the subscript. For example, p x phi here actually means p of x equal to phi, and here also p of y equal to 2. For joint probabilities, we write p of x taking a value lowercase x, and p of y taking a lowercase y. So this is a joint probability that the variable x taking the value x, and the variable y taking a value y. We can simply just write p of x and y. Each random variable has a probability distribution which defines how likely the variable is to take a value or a range of values. The structure of the distribution depends on whether the distribution is discrete or continuous. The distribution of a discrete variable looks like the graph on the left side, and the distribution for a continuous variable looks like the graph on the right side. Now first, let's look at discrete distributions. Now, what is a probability mass function? A probability mass function, or PMF, for discrete random variable is a mutually exclusive list of all possible numerical outcomes and associated probabilities. In the example, the variable x is the interruptions per day in computer network. The outcomes may be 0, 1, 2, 3, 4, and 5. In the other column, we have the associated probability. Basically, it is a probability of the variable x taking the value on the left side, and sum of all the probabilities on the right side is equal to 1. Here are the properties of a PMF. The probability of the a variable taking a value x, or p of x, is greater than or equal to 0 for every real number x, and sum of p of x for all x is equal to 1. Now we talked about the cumulative distribution function, or CDF. This function associates each value x and the probability that the variable x is less than or equal to that value. When we write x, f of x, it means the probability of the variable x less than or equal to the lowercase x value. In the example, let's have x as the sum of the dots when you throw two dice. The range of x is from 0 to 13. In column 3, we have the probability of x, p of x for each value of x on the first column. The cumulative distribution function f of x is in the last column. Looking at this column, we can see each value of f of x is actually a cumulative sum of all the previous values in p of x. Taking point 17 as an example, it is actually the cumulative sum of all the values from the first, the second, the third, the fourth, and the fifth, which are 0, 0, 0.03, 0.06, and 0.08 in p of x column. Here are the properties of a distribution function. F of x is greater than or equal to 0 and less than or equal to 1. The second property is that the limit of f of x as x approaches infinity is equal to 1. And also the limit of f of x as x approaches negative infinity is equal to 0. The distribution function is a non-decreasing function. Roughly speaking, you see the function keeps increasing and decreasing. It is right continuous. When you are asked for the probability of x less than or equal to a value b and greater than a value a, simply it is just f of b minus f of a. And probability of x greater than a is actually 1 minus the probability of x less than or equal to a, or 1 minus f of a. Let's look at the division of PMF and CDF. So let's say we have x as the number of months in the first 3 months of the next year that your stock portfolio increase in worth. In the PMF function, we have months 0, 1, 2, 3, and associated probabilities 1/8, 3/8, 3/8, and 1/8. In the CDF function on the right side, we simply cumulatively add up all the previous probabilities. For example, in month 0, we have 1/8, which is simply the probability in month 0 in the PMF function. Now in month 1, we add up the probability of month 0 and month 1. So they are 1/8 and 3/8. So the sum is 4/8. Keep proceeding this way. For month 2, we have 7/8, and for month 3, we have 1. We denote the expected value or mean of a discrete variable, mu. Mu is the expected value of x, e of x, and is equal to the sum of each possible value xi times the associated probability, and the sum is for all xi from 1 to n. Now, taking the same example from the previous slide, we add a new column, which is xi times p of xi. So going through the table, vertically from the top to the bottom for each value of xi and each associated probability. We get one row which is the product of xi and the associated probability. So sum them all together, we have the expected value mu or e of x, which is equal to 1.4. We talked about the central tendencies with the mean previously, and now we talk about the dispersion of a discrete random variable. What is a variance? The variance of a discrete variable is denoted as sigma squared. Sigma squared is equal to the sum from 1 to n, and n here is a sample size. For each value xi, we measure the difference between xi and the mean and take the square of it times the associated probability for that value. Standard deviation of a discrete variable simply is the square root of the variance. Now let's take the same example from the previous slide. Now let's see how we can calculate the variance. So here we add the new column in the last column. To make it easy to track the calculation, we also add a column for the difference squared. So for each row, each value xi and the associated probability, we get the difference squared, and the difference squared times the associated probability. Sum them all together, we have the variance sigma squared, which is equal to 2.04, and the standard deviation basically is the square root of sigma squared, which is about 1.4 something. Due to the commonality of certain probability distributions, mathematicians and statisticians have defined and studied families of distributions. So this makes it easy to sample or calculate the central tendencies and also the dispersion. Also allows for easily modeling a number of situations. Mostly we will look at binomial distribution and Poisson distribution.